All right, so we're going to now talk about Titanic and its connection to machine learning, because it has a connection, apparently. So if you don't believe me, you must just see for yourself by the end of this session. So there's a data set on passengers of Titanic and whether they survived or not. So we have one variable, survival, which is either no or yes, 0 or 1. Passenger class, 1, 2, and 3 for first, second, and third class passengers. Name, sex, age, number of siblings or spouse, number of parents and children aboard on the ship, ticket number, passenger fare, whether they had the cabin or not, and port of embarkation, whether it was Cherbourg, Queenstown, or Southampton. So for loading the data, we can use this wget and load the data into the storage of this Google Colab, like with this code. So you can see that the CSV file is loaded here. It's here. Second option is to just download this CSV file and then upload it to the session. Now that the file is there, we can just load it as a CSV file and read it line by line and append these lines into a list. Then we get a list of lists. So this is a data structure which is perhaps very easy to think of, but as we see, it's not the best data structure for our purposes. So now that we have this list of lists, our data looks like this. We have a list. In this list, each entry is a list itself. For example, this is the first row of the data, which are these column headers, and it is an entry of the first list, and it is a list itself. If we want the first row of the data, we just provide raw data index 0, and it provides the entry at index 0. If we want the first two samples, we use 1 to 3. 1 is included, 3 is excluded. So in Python, whenever we provide a range, the second number is excluded. So we get passenger number 1, their information, and passenger number 2. If these are too simple, let me know, so that I go over these parts more quickly so that we can explain and discuss the more exciting parts more. No? Okay. So if we want the last 5 samples, we can provide -5, and then it kind of counts from the end of the table, right? So if this is our table, the last row will be -1. The second to the last row is -2. That's why -5 means that we are getting the last 5 samples. So we get the passenger number 887, 888, 889. So the total number of passengers was 891, and we got all those last 5 passengers. If we want the first 5 out samples, we can provide a range like 1 to 10, and then the step size. Then it's going to print passenger number 1, then 3, 5, 7, and 9. So in this sense, a list of lists is useful. But for example, if we want some passenger whose passenger ID is 194, we will just try this index, but it's really just up to whether there's some structure to this data. It's just going with the luck that every row has like a consecutive number, and row number 194 happens to be passenger number 194. So in this case, we were lucky, but a list of lists is not as useful as a data structure, especially in the context of machine learning. So Numpy, a Numpy array is a much better data structure. So we can load the data and save it as a Numpy array. Then if we print the data, we get this two-dimensional array, which is just like a matrix. So a matrix has rows and columns, and you can see that the first row of the data becomes the first row of this matrix, and so on. The second row is here. The last row, which was last passenger, is here. And with a two-dimensional array, we can also refer to the columns. So now if we want a certain column of the data, it's very easy with a Numpy array. So indexing and slicing between list of lists and Numpy array would be pretty much the same if the data is one-dimensional. But for two-dimensional data, as we're going to see, there are some differences. So one-dimensional data, if we have a list like this, it doesn't really matter if we refer to it as a list or as a Numpy array. So for example, if I want entry at index 2, I can call it like this. If I want to slice the list to get the first 8 rows of the data, first 8 entries of the data in step size of 2, I provide this, and these are the results. You can see that for variable at index 2, I get 3. Why is that? Because in Python, counting starts from 0, which is how it should be. People who are used to R, they complain about this, while everything in counting in computer science starts from 0. So the natural thing is to start from 0. I don't know why some other people complain about the issue with counting from 0. To me, it's natural. So if we provide this line of code, it gives us 2, 4, 6, and 8, which are, of course, entry at index 1, 3, 5, and 7. So we went from 1 to 8 in step size of 2. And with a Numpy array, with the same code, we get this pretty much same result. You can see this is now a Numpy array of the same data. When I provide this, again, I get value 3. And when I provide this, I get this. Just the commas are missing, which doesn't matter. That's just for printing. So you can see that for one-dimensional data, everything is the same, which gives us the kind of false sense of security that everything remains the same also for two-dimensional data, and unfortunately that's not the case. So two-dimensional data, if we have 3 rows of data like this as a list of lists, and we want to index it, we need to provide 2 indices, right? So we provide 2 and 0, and we see what we get. So we got 9. Can someone explain why we got 9? It's a bit confusing to me. Yeah. Right, that's right. So Python starts from the left. First, it kind of takes care of this part of the code that says in list variable, give me entry at index 2. This is entry at index 0. This is entry at index 1. And this is entry at index 2. Then, for this whole thing, which is a list itself, then we want entry at index 0, which would be this. Then for slicing, again, we can provide 0 to 2, and then 0, and then we get 1, 2, 3, 4. This is because when we first slice the list from 0 to 2, it creates a new list that has these 2 entries in it. And then from that list, then we ask for entry at index 0, which would be this, and it is printed here. But with a two-dimensional NumPy array, you can see that pretty much the same command leads to a totally different output. I mean, in case of indexing, it's the same thing. Again, we get 9. But in case of slicing, the result is different. We get 1 and 5. Can someone please explain how this command leads to this? Raise your hand if you want to answer. Yep. Yep. That's right. So with NumPy array, we need to provide row indices and column indices. For rows, we said 0 to 2. 2 is not included. This means rows 0 and row 1. So first, NumPy is going to get this row and this row. But that's incomplete. We also need to provide columns. So we want entries that are at column index 0. So we get 1 from here and 5 from here. And they are reported here. So just these small differences sometimes lead to bugs that are a bit challenging when we start working with NumPy and these data structures. All right, if we want the first row with NumPy, we can just provide row number 0, and for columns, whatever, right? So this thing, when we also don't provide it, it means whatever. Either case, it just gives us the first row. For first column, which is very difficult to get in a list of lists, in NumPy, we just say whatever for row, and for column, it has to be column 0. Any questions? Are these somewhat useful? Yeah? Okay, good. So we're going to get to more exciting stuff a bit later, back to Titanic and Jack and Rose. So if we want the first 5 columns and 5 rows, we can, ask for the top left part of the data like this. So for rows, this thing is the same thing as 0 to 5, right? Beginning to 5 or 0 to 5 is the same thing. So if we want to transpose the data, again with NumPy is super easy. If it was a list of lists, it would be really challenging to transpose the data. Sometimes you want to do some row operation, and there's a command for it if that row was a variable. Then the way to do it is to transpose the data so that your row becomes a column, and then do the operation, then transpose it back. So if we want to see, where, what are the indices of entries matching some condition, we can use mp.where. For example, if this is our data and we want to see what are the entries that are larger than 7, we can use this, and then it returns row indices and column indices. So it's a bit cryptic, but we need to consider that this one corresponds to this one. So there is an entry at row number 1, column 3, that matches the condition. So the condition was value being larger than 7. This is row index 1, and this is column 3, right? All the other ones are row number 2, different columns of that row. All right, if we want to see what is the index of the column where 6 variable is stored, this is the kind of proper way to do it. We use mp where and then it gives us 4. The lazy way to do it, which is how I would approach it, is just printing the first row of the data and counting 0, 1, 2, 3, 4. So for me, this is the natural way to do it. This is, I guess, how I should formally teach. But I just have an inclination to just go with this. It's just more intuitive. So, but sometimes you work with some data that you cannot print, right? It's large, or printing it takes time, or there are other issues. That's why I guess there's also some advantage in learning the proper way. All right, if we want to see what is the index, what are the 2 indices of where this name appears in the data, we just use np where, and it says 194 and 3. So now from this we can see, even if the data is kind of shuffled or something, now we don't need to just go with our luck, right? It just confirms that row number 194 and column index 3 is where the data matches this name. Now we can also retrieve the name by index. It's the opposite of the previous operation. If we want to see, if we want to get the indices of all male passengers, right? We can just use this to see where the string matches male, right? And then the length of the list of those indices tells us how many male passengers we have. And then if we divide it by the total number of passengers, we get the percentage of male passengers. So these are the indices. For example, passenger in row number 660 of the data was a male passenger. In total, length of this list is 577. And when we divide this by the total number of rows, we can see that these many of the passengers were male. So you can work on this later on, very similar. If we want to see, let me just clear the output. All right, if we want to see indices of passengers who survived, we just ask for np where. We want to know what column has the survival information in it. This is, again, the proper way to do it. Lazy way to do it is like this, 0, 1. Now, you can see that we're repeating something, right? So whenever you are programming and you see that you're doing something twice, that's the right time to ask yourself, should I just automate this? So if we want to automate this, we can just define a define a dictionary and store all those column headers as keys of that dictionary, and the column numbers, column indexes as the values of the dictionary. So we define fields. A dictionary is like this with curly brackets. This is key and this is value. So whenever we use this dictionary and provide passenger ID, it returns 0. That's how we can know later on, for example, if we want to know where age is, what is the index of the column where age is stored, we just provide fields age. So let's say we want to know the percentage of male passengers who survived. So first we need to get the indices of male passengers, get the indices of survived passengers. Then we have 2 lists, and the intersection of those 2 indices would be indices of passengers who were male and survived. So, but for the intersection, we need to convert these lists into sets. So here I'm getting the indices. This is, for example, the set of the list of indices of those who survived. For example, the passenger in row number 721 survived. Now, if I intersect this, the set of this list to the set of male passengers, that would be set of passengers who were male and survived. So this is set of male indices, set of survived indices, and here does the intersection for us. So you can see that 18.8% of male passengers of Titanic survived the accident. All right. Now we can define a function, get survival, to automate this even further, so that if we want any sort of calculation on survival for some characteristics, we can just provide those characteristics in this function, and then it finds those sets of indices, intersects them, and then divide them by the total, and that's how we can answer different questions. So you can see that this function does the things that we did a bit earlier in our script, but now in a proper functional programming way. So now I'm using this function in the same chunk of code, which is not a good practice. So you can see that we can get the same number using the function. Now that we have this function, if we have other questions on what percentage of female passengers who were from the first class survived, if you're interested in that, we just use this function that we defined and provide these characteristics as the input, and it tells us that 96.8% of passengers who were female from first class survived. This is why Titanic is a story of class and gender, because whether or not these people survived had a lot to do with their gender and with their ticket class, which is a representation of their socioeconomic status, right? So as you can see now, there's some pattern, some regularity in the data, because if I ask you, what is your prediction on a female passenger from first class on Titanic? Do you think they survived or not? What would be your prediction? You would say survived, because it's 96.8%. So the same thing is learning from examples. If we just provide these examples to the machine so that we train the algorithm, it's going to capture these regularities, and later on, if we ask, if this specific passenger with these characteristics survived or not, is going to look at, the kind of regularities that it has captured and give us a prediction. So there are a couple of, other questions that you can work out on your own later on. Now let's move on to cleaning the data set. So apparently something around 80% of time of a data scientist is spent on data cleaning. But data cleaning is not fancy and not exciting. That's why people don't talk about it as much as they talk about deep learning and how AI is revolutionizing everything. But now, in this class, let's also do the realistic part of some data cleaning. So if we have a list like this, and we want to replace the entries that are larger than 5 with 100, this is one way to do it. We can say, we can provide the condition in square brackets, and you can see that the list is changed. This Numpy array is changed such that these entries are replaced with 100. So sometimes we use something like this for data cleaning. We want to convert these strings into numerical values. For example, under the variable sex, we have male and female. We can replace male with 0, female with 1. So you can see that then the data looks like this. These are still, strings because they are in quotation. We can then change them to floating point numbers, right? If we change them to floating point numbers, then we can also do other kind of numerical operations on them. We can get the mean of this list or add these numbers and so on. So these are usually needed for data cleaning. Also for age, in our data set, there were some passengers whose age was not available and they were stored as empty string, right? So we want to replace these empty strings by np.nan, which means not a number. So this is the proper way of recording missing information in Numpy. So here I'm just replacing them with nan, but you can see that they are still string. This is because each entry of a NumPy array only has one format. So we can then convert these into numbers in the next step. Yeah. Yeah. This is something that you should decide on your project to see which one makes sense. Here, I'm just telling you about the method, but you see that we're going to now replace them with 0, but possibly replacing them with the mean value would be a better idea. Yeah. That's one reason. Another reason is that we want to plot age. For example, we want to get a histogram of age distribution of the passengers. If they are strings, we cannot plot them. Yeah. Then if we want to do learning on them, again, our machine learning model takes in values as features, so we cannot provide a string of male and female. Instead of that, we need to provide 0 and 1. Just like in regression, right? You define, I guess, dummy variables, right, for categorical variables. So this is the same thing. So here I'm also converting them to floating point numbers, and you can see that now they are not strings anymore. And these nan entries, we can replace them with 0, or we can replace them with the mean, as your classmate suggested. Actually, this is in the next chunk of code, and you can figure that out. But it's very similar to the previous chunk of code. All right, so now if we want to kind of bring all of these together, we can define a class, call it Titanic data, so that next time that we want to load this data, we just run some functions from this class and it takes care of the data cleaning for us. So a class is defined like this in Python. It has this part for initialization, and then there are different things that you define within a class. For example, you define function. For example, here we have get survival function, which we define within our class. Later on, when we just load this class, we can use this function. Here is another function, clean data, and then we have clean that can be used to convert these empty strings to 0, or these empty strings to Numpy nan. So when we define this, now next time that we want to work on this data, we're not going to run all the previous chunks of code. We're going to just load the CSV file and then use what we have in our class. So this is, object-oriented programming. So here you can see that I'm calling this class on the CSV file, right? And then I'm cleaning the data. So this is the raw data that is loaded with the class. Then the data is cleaned. For example, here mail is replaced with 0. For example, S, which was city of Southampton, is replaced with 2. And then also in our class, we had a function, keep columns, which was a function that we provide indices of some columns so that we keep them for prediction purposes. So let's say these are the columns that we want for prediction. For example, ticket number is not relevant for predicting whether someone survives or not. So these are now the numeric values related to this passenger, which we keep for making a prediction. So these are raw data about this passenger. For example, they belong to class 3. This was their name, male, 22 years old, right? This was the ticket number. This was how much they paid for the ticket. And we have no information about whether they had cabin or not. And they got on the ship in Southampton. For the machine learning model, this is not useful. The machine learning model wants these numbers. Instead of Southampton, the machine wants to see 2. Instead of male, the machine wants to see 0 in order to be able to make a connection between these numbers. All right, so then our feature data looks like this. This is what we call, design matrix. In regression term, the first column here is y, and everything else are just predictors. Each column is a predictor. This one is like some x1, this is some x2, and so on. So this is just like multivariate regression. All right, so the columns that we kept for making prediction are class, sex, age, number of sibling and spouse, number of parents and children aboard, ticket fare, and port of embarkation. All right, so there's also some parts about visualization, which is just very basic. So I leave it to you to explore that on your own. It's just about bar plot and histogram. I'm pretty sure that you know these things much better than me. So let's move on to the machine learning part. All right. So far we tried list of lists and Numpy, but another data structure which is very useful for machine learning is a Pandas data frame. So Pandas data frame allows us to load the data directly from the URL. So from this URL, you can see that I'm loading the data directly. If I want the first 5 rows, I use .head. It prints the first 5 rows very nicely for me, as you can see. There are many operations that are so convenient in Pandas. That's why, when you get used to it, it's just difficult to work with other data structures. It's kind of addictive. So if we want to see indices of columns, we just use .columns. So that's another advantage in Pandas, that many things are just so natural, so intuitive. If we want the data types of each column, we use .dtypes. and it tells us that passenger ID is loaded as an integer, name is loaded as an object. So who can tell me what does this mean? What does object mean here? Yeah? It means a string here. So name of passengers are loaded as a string, which is fine, but for example, sex is loaded as string. Also here, cabin is loaded as string. So we want to make some changes to this, right? So also .info tells you how many of the, how many missing values you have for each column. For example, for column age, we have 714 non-null values. The remainder would be null values. For cabin, we only have information about 204 passengers. For port of embarkation, you can see that there are 2 missing values. All these other ones, where we have 891, it means that we have data for every single passenger. All right, .describe gives us max and mean and count and these sort of summary statistics if we have quantitative variables. If we want to slice a pandas data frame by column, it's very convenient. We just provide the column names in a dictionary, and it just gives us that part of the table. If we want to slice by row, first we provide this, which means whatever for column, and then 10 to 20 means that we want rows number index 10 all the way to 20, where 10 is included, 20 is not included. So you can see that we get 10 rows of the data. Or we can slice by row and column at the same time, just like this. Then it's going to give us 3 specific columns and 10 specific rows. All right, so I guess we're running out of time. I'm going to just go a bit faster here. If we want, passengers matching a certain condition, for example, those younger than 1, again, you can see that the code is very, close to human language. It is as if, there's a panda here in this computer that speaks English. So we just say, data pandas age less than 1, and it does the job for us. So that's another advantage of pandas. So if we want, passengers who are female, younger than, let's say, 15, so this should have been 15, from class 1, we can provide these as intersection of some, Boolean operations. Each of these is true or false, and then and here is just logical operator. So if all of these 3 are true, then the passenger matches all the conditions that we want, and it will be returned to us. So you can see that there were exactly 2 passengers who were under 15 years of age in class 1 and female. We can also sort the data using .sort value. This returns a sorted data frame, but the sorting is not in place. If you want to be also saved, you need to select in place equals true. Or you can just overwrite it to the same thing. So here I'm sorting by age, or we can sort by 2 different variables. For example, sorting by class and then by age. This one in ascending order, this one in descending order. You can see that it's very convenient. All right, so these were just some basic stuff in Pandas. We can save to CSV file if we want. We can fill all the missing values using .fillNA. I cannot think of a data science project that I've done without using this. Hopefully not always replacing everything with 0. That's just too irresponsible. But usually when you work on a real project, there are, some missing values and you need to do something about them. And actually one of your reading assignments is, has some components on data cleaning and handling missing values. All right. So here we replace every single missing value with 0. And now if we use .info, it says that all the columns are all the entries exist. Yeah. 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 But yeah, I guess if it is a string and then you're also filling some variable which is integer, probably you get an error or something. Yeah. Either you get an error or some undesired output. I guess error is even better, right? So if we want to replace, these categorical values to numeric values, we can use a dictionary and use .replace. So here, male and female are replaced to 0 and 1. Here, these cities, they are replaced to 1, 2, and 3 for Cherbourg, Southampton, and Queenstown. And now you can see that, the data is getting closer to what we need for machine learning. For example, embarked, which was port of embarkation, is integer. You can see that sex is integer, right? Now, let's say these are the columns that we want to keep. So this would be now our design matrix, right? So this column here is Y. Everything else are predictors. So similar to how you can fit a multivariate regression model on these columns to predict survival, you can train a supervised learning model like decision trees or random forests or support vector machines and make predictions on survivals. So there's also some parts on visualizing data. You can check them later. Let's move on to machine learning part. So what I promised you. So let's say that we want to make prediction on this data. So here you can see that we have these many rows and these many columns. So the process data looks like this. This is now in a Numpy array, and it is our design matrix is what we provide to the machine. And it makes the connection between these numbers. So for supervised learning, we need to split the data. So I'm splitting to training and validation. So here, 712 rows of the data are used for training, 179 for validation. We're going to learn more about this later on in the course. It's just more convenient, but you can also use Pandas data frame. Yeah. So now our data looks like this. All of these are X's, predictors, and these are response or Y values, right? So the idea is predicting these zeros and ones, which was unfortunately fate of, some people. So with scikit-learn, now we're going to train decision tree, KNN, random forests, and support vector machines and see which one does a better job of making predictions. So for decision trees, we're going to learn more about them later in the course, but fitting them to the data is very easy. We just use model.fit. That's it. Now it's ready to make predictions, and we can use it to make prediction on the training data. These are the the true values of response, whether these 10 people survived or not, and these are the predictions. You can see that our decision tree does an excellent job on the training data, which is not that exciting, given the fact that decision trees can just overfit to the data. So these are the things we're going to discuss on Friday. Now let's look at the performance on validation data. So this is the validation data. You can see that the machine learning model makes one error here. This was a passenger who actually survives, but according to our prediction, they do not survive. But for evaluating performance, we need to look at percentage of matching, classes. So for all the validation data, you can see that on 79% of the validation data, the predictions were correct. So this is a measure of performance of the model, 79%. Not that bad. But on the training data, the performance, as you can see, is much better. But the thing is, evaluating performance on training data is like cheating, because we're evaluating the model on things that it has seen before. So if it has just memorized everything, it does 100% in here, which is not a good sign. So here we have 79%, which is a more relevant evaluation of performance of the model. All right, let's now try KNN and see how good it does. KNN is 71% accurate. You can see that the code is very straightforward. Fit and then predict. Another decision tree, this one 81% accurate. And if we run it again, as there's some stochasticity in here, you can see that each time the model that is trained has slightly different performance. Also, if you're running it on your machines, possibly you get a different value unless we fit the same random number seed, so that all the random processes in our machines would be the same. A random forest should perform better. 78%, so not that exciting. Support vector machines, 70%. So you can see in machine learning, in many situations, there are a wide range of models that are available to you, and the question is which one is more useful, which one is more suitable for your task, and that's one of the main things we're going to learn in this course. Because just trying models is as easy as we saw.